Hello, in this video we will discuss a phenomenon called rolling motion of a rigid body or object. So take a look at this graph, which is not even a graph, is actually a photograph, a long exposure of a cylinder that is allowed to roll on a surface, and that cylinder has a source of light that is red here and a source of light that is green at the center, so here. So this object is allowed to roll. It's not just moving, it's rolling. And this is a very special type of rolling, is rolling without slippage or slipping, which means which means the relative motion of the tires or the surface. Let's say this is not a tire yet. The surface here with respect to the ground is zero. This particle is at rest with respect to the ground. As it rolls, well, this particle now is going to touch, and then this particle is going to touch, and then this particle, right? But at all times, this particle, so at all times, the relative motion of whatever point in the cylinder is touching the ground, the relative velocity is zero, all right? Okay, so as it rolls, the green line, well, just follows a line. That's the translation. That's a translation motion, of course. Okay, but the red one, well, is this point, as we can see. Let's put the red again. This point, well, is going like this, as we see in the thing. So there, as we can see, oh, by the way, this type of red line, the red line is called a cycloid, and is what I remember when I told you about the planets. Remember that they thought the Earth was at the center, and then the planets will do something like this around us. Well, this is a cycloid path. But anyways, so the motion is very complex, right? So to understand rolling motion, we can focus on the center of mass. First thing we can recognize is that the object has translational motion, right? Plus the rolling. So we're going to basically divide the motion in two. You'll see. Here is the cylinder again. This is the center of the cylinder here. Notice that as the cylinder rotates, an angle theta, right? So so this point touches first, and then eventually this point is here. As the cylinder rotates an angle theta, the center of mass went from here to here, which is of course at the same distance as the segment of arc. You see how this point is here? So that means the displacement of the center of mass is equal to S, is equal to the segment of arc subtended between these two radii. So that will be S, which means r theta. So that's the displacement. The displacement is S. This distance here, well, of course, is the same one here, is S. So if that's the displacement, what about the velocity? Well, the velocity, well, let me put it more clearly. The velocity of the center of mass, well, will be dx over ds, but over dt, but we already said that x is s, so ds over dt. So we did already this in class. That will be r d theta over dt plus theta dr over dt. But the radius is not changing, so this is 0. So the velocity of the center of mass is r, and d theta over dt, that's omega, right? If we only look at the magnitude, then that's the magnitude. It's the speed of the center of mass is r omega. And this happens when you have a condition called pure rolling. Pure rolling, again, it's when there is no slipping, right? I'll demonstrate this in class. To find the acceleration of the center of mass, well, we have to do the derivative, take the derivative again, which is going to be derivative of r omega with respect to time. So r d omega over dt plus omega dr over dt, but this again is 0. So the acceleration of the center of mass is r alpha. And I know this looked a lot like these two equations we saw before, okay, but they're not necessary. This is the velocity of the rim of the cylinder, and the acceleration tangential. Actually, I should put here t and t. The tangential the speed and the tangential acceleration at any point, basically. If r is the whole radius, then it's the rim, but it could be anywhere here, right? And then these equations, which look almost the same, are the speed and the acceleration of the center of mass of my object that is rolling. So let's say the object is in pure rolling. What I'm going to say is that an object rolling, pure rolling, is the equivalent of having the same cylinder just moving to the right. Pure translation plus the object just rotating. Pure rotation. So pure rolling without slippage is the same as pure translation plus pure rotation. Well, with a better drawing, we can say the opposite. The pure rotation plus pure translation is equal to this, which is the combination of translational rotation, and that will be pure rolling. Now, if you are only rotating, well, the center of mass is not moving. So the tangential speed on the rim here will be just Vr omega. Down here is Vr omega, right? These are tangential speeds opposite to each other. We will have, of course, the same here. Let me put it here. We will have the same V here and the same V here and the same V everywhere. R omega, okay? But I'm just going to erase this so it's not confusing. If you have pure translation, then nothing moves, nothing has angular motion. It's all linear motion. The center of mass, this point, that point, this one, all points are moving at the speed of the center of mass. So if we add these two motions, this plus this, we get rolling motion, right? And notice what happens. Let's consider point by point. If we add this point plus this point, you see they cancel out. So the point that is in contact with the floor is not moving. That's what we call pure rolling, remember. This point is not moving. You see the combination of the rotation plus the translation gives you 0 down here. At the center of mass, here this is 0 and this is VCM. So of course, when we add these two, the center of mass moves at the speed VCM, speed of the center of mass. Up here, we have tangential velocity because of the rotation, and we have velocity because of the translation. So when we add them, we see twice the speed. So instantaneously, what's going on is this cylinder is pivoting about this point, right? An instant later, of course, this point is going to be here. The center of mass is going to be here. So, well, it's moving. But with respect to the pivot, the center of mass moves at r omega, and the other edge moves at twice r omega. Look, what is the kinetic energy of pure rotation? We already did this, is I, so 1/2 I omega squared, right? Remember, the equivalent was 1/2 mv squared. That's the translational kinetic energy, but actually I'm going to put it here. Is 1/2 mv squared. Just out of pure translation, this is the kinetic energy. Out of pure rotation, I can put it kr is 1/2 I omega squared. Instead of m, I put moment of inertia. Instead of translational speed, I put angular speed. So if I want the kinetic energy of the rolling object, well, it's going to be these two. 1/2 I omega squared plus 1/2 mv squared. That's the energy of the rolling object. Kinetic. This is, of course, the velocity of the center of mass, right, as we see here. I can work this a little bit more by remembering that omega, we saw the velocity of the center of mass was r omega, right? So here, instead of writing omega, I'm going to write velocity of the center of mass over r. So instead of omega, I'm going to put velocity of the center of mass squared over r squared. And then plus 1/2 of the mass times the velocity of the center of mass squared. So this is one flavor of the kinetic energy for a pure rolling object. We can do also the opposite. We can leave the first term in terms of omega squared, and then the second term, put it in terms of, instead of velocity or speed of the center of mass, we can put r squared omega squared. So two flavors for the kinetic energy of the rolling object. Combination of rotation and translation. This one in terms of the center of mass, the speed of the center of mass. This one in terms of the angular speed. So in fact, three flavors: 1, 2, and 3. And to be very clear, this has to be the moment of inertia with respect to the center of mass. I should have written this before. Remember that there is the center of inertia changes according to the axis, if it's around this axis, or if it's here, or it's here. But for this case, is the moment of inertia measured or calculated around the center of mass. So there you go. Consider this object. For it to roll down the incline, you need friction. Without friction, this thing will just glide, but we don't need this to glide. We want it to roll. So friction needs to apply a force, so that creates torque, so the thing actually rolls. Now you will say, what about the mechanical energy? Well, the mechanical energy, which is kinetic plus potential, is conserved even if there is friction. How can this be? I'm telling you there is friction and that the mechanical energy is conserved. Remember, friction is non-conservative. So the reason energy is conserved is because there is no relative motion between the particles being acted by friction. No relative motion. In a car, in reality, there is deformation of the rubber, right? You see that this tire is not perfectly flat. There is deformation. That deformation is plastic, so that does convert energy into internal energy. So there is some mechanical energy that is not conserved in the real world, but we are not going to study that. Only this type. This is called rolling friction, and it's not part of the syllabus. So we're going to practice these problems in class.